Hi, I'm Bob. Welcome to the computer exercise part of the chapter on the limited dependent variable models and sample selection corrections. I will use data to solve all the computer exercises. I hope the solutions help you better understand this chapter and have an idea of how the empirical analysis is carried out using the methods we have learned from this chapter. Let's find answers to computer exercise 1. In part 2, we will estimate the model from part 1 by OLS. Test the null hypothesis beta 0 equals 0 against a two-sided alternative. Use both the usual and heteroscedasticity robust standard errors. We use the linear probability model to estimate beta 0 and beta 1 by OLS. We use the regress command in Stata to do that. Then we use the lincom command to test the null hypothesis. The command lincom means a linear combination of parameters. The lincom command is followed by the linear combination we want to estimate and test. Here the null hypothesis is beta 0 equals 0.5. So we type lincom underscore constant minus 0.5. We obtain the estimate of the linear combination and its t-statistic. The t-statistic is 2.73 and its p-value is 0.007. It is statistically significant at the 1% level against a two-sided alternative. We reject the null hypothesis that beta 0 equals 0.5 at the 1% level. Next, we use the heteroscedasticity robust standard errors in the linear probability model estimation. We add the variance-covariance matrix option for the regress command and then use the lincom command again to test the null hypothesis. The t-statistic is slightly smaller than the usual standard error case. The t-statistic is 2.43 and its p-value is 0.015. We could not reject the null hypothesis that beta 0 equals 0.5 at the 1% level, but we could reject it at any level above 1.5%. In part 3, is spread statistically significant? What is the estimated probability that the favored team wins when spread equals 10? The variable spread is statistically significant at the 1% level, with a t-statistic of 10.08. according to the linear probability model with the heteroscedasticity robust standard errors. When spread equals 10, we can plug the value in the estimated equation and obtain the predicted probability that the favored team wins. It is 0.7706. Or we can use the margins command in Stata to find the predicted probability at a specific point. We type margins and a comma, followed by the at option. We put the value of the explanatory variable at which we want to predict the probability inside the parenthesis. Here we write spread equals 10. We have the same answer as we calculated manually. The command also provides the significance of the prediction. In part 4, we estimate a Probit model for the probability. Interpret and test the null hypothesis that the intercept is 0. We use the Probit command in Stata to estimate the Probit model. The p-value for the null hypothesis that the intercept equals 0 is 0.9. We failed to reject the null hypothesis. In Part 5, use the Probit model to estimate the probability that the favored team wins when spread equals 10. Compare this with the linear probability model estimate from Part 3. We still use the margins command in Stata to compute the predicted probability at a specific value of the explanatory variable. The predicted probability is 0.820, which is higher than that from the linear probability model. Of course, we can calculate it manually using the standard normal cumulative distribution function. In Part 6, add the variables of whether the favored team is at home, whether the favored team is in the top 25, and whether the underdog is in the top 25 to the Probit model and test the joint significance of these variables using the likelihood ratio test. Interpret this result, focusing on the question of whether the spread incorporates all observable information prior to a game. We add the 3 explanatory variables to the Probit model. We use the estimate store command to store the results of the full or unrestricted model. Then we estimate the restricted model. The restricted model is to set the 3 explanatory variables equal to 0. We also store the results. After that, we use the LR test command to perform the LR test. The likelihood ratio statistic is 1.84 in a chi-square distribution with 3 degrees of freedom. This gives a p-value of 0.61. We could not reject the null hypothesis that the 3 explanatory variables are jointly 0, which is evidence that the spread incorporates all observable information before the game, and the other observable factors have no additional prediction power for the probability of winning. The options for the LR test are to display more information on the 2 models. We can do the LR test by hand too. The LR statistic equals 2 times the difference in the log likelihood between the unrestricted and the restricted models. It follows the chi-square distribution under the null hypothesis. We reach the same result as using the LR test command in Stata. Let's go to computer exercise 2. In Part 1, estimate a Probit model of approve on white. Find the estimated probability of known approval for both whites and non-whites. How do these compare with the linear probability estimates? We estimate the Probit model and then use the margins command and the add option to find the predicted probability of approval. It is 0.91 for whites and 0.71 for non-whites. We can also compute it by hand using Stata's standard normal cumulative distribution function. By contrast, we estimate the linear probability model. The predicted probability for non-y's is the intercept, and the probability for y's is the sum of the intercept and the slope coefficient. They are 0.71 and 0.91, respectively. They are similar to those from the Probit model. In Part 2, we add 14 explanatory variables to the Probit model. Is there statistically significant evidence of discrimination against non-whites? After adding the variables to the model, the white variable is still statistically significant at 1% level. There is still evidence of discrimination against non-whites. We can compute the average partial effect of whites on the probability of approval using the margins command and the dydx option. The average partial effect is 0.086, meaning that whites have an 8.6 percentage points higher probability of approval than non-whites, holding other factors constant. By contrast, the linear probability model gives an average partial effect of 0.129. In Part 3, estimate model from Part 2 by Logit. Compare the coefficient on white to the Probit estimate. We estimate the Logit model and obtain the average partial effect of the whites on the probability of approval. It is 0.083. It is close to that from the Probit model, 0.086. In Part 4, use equation 17.17 to estimate the sizes of the discrimination effects for Probit and Logit. We have already computed the average partial effect for Probit and Logit. It is around 0.08. The whites have an 8 percentage points higher probability of approval than non-whites, other things being equal. Let's do computer exercise 3. In Part 1, for what percentage of the workers in the sample is pension equal to 0? What is the range of pension for workers with non-zero pension benefits? Why is a Tobit model appropriate for modeling pension? We use the summarize command to find information on the variable pension. We use the count command to find the number of zeros. Out of 616 workers, 172 workers have zero pension. It amounts to 27.9%. The range of pension is from $7.28 to $2,880.27. It can be seen as a corner solution response. The pension variable is 0 for a non-trivial fraction of the population, but is roughly continuously distributed over positive values. A Tobit model is appropriate in this case. In Part 2, estimate a Tobit model explaining pension in terms of experience, age, tenure, education, dependence, married, white, and male. Do whites and males have statistically significantly higher expected pension benefits? We use the Tobit command to estimate the Tobit model. The lower limit option specifies the corner value, which is 0 in this case. The coefficient on Ys is not statistically significant at the 10% level. The coefficient on the male is statistically significant at the 1% level. The estimate is $308. After adjustment, males have about 229 more pension benefits than females, holding other factors constant. In Part 3, use the results from Part 2 to estimate the difference in expected pension benefits for a white male and a non-white female, both of whom are 35 years old, single with no dependents, have 16 years of education, and have 10 years of experience. We use the margins command and the add option to compute the expected pension benefits. We put in the value for each explanatory variable. There is no value for the tenure variable. I use the sample mean. The white male's expected pension benefit is $893. And the non-white female's pension is $522. The difference is $371. In Part 4, we add the variable union to the Tobit model. The estimate of the coefficient on union is 439. It is statistically significant at the 1% level, with a t-statistic of 7.03. In Part 5, apply the Tobit model from Part 4, but with the pension earnings ratio as the dependent variable. The gender or race have an effect on the pension earnings ratio. We estimate the Tobit model and find that gender and race are both statistically insignificant at any reasonable level. It implies that the findings in Part 3 that white males have more pension benefits than non-white females are due to higher earnings for white males. Let's do computer exercise 4. In Part 1, we add 3 terms to the Poisson regression in example 17.3. We use the Poisson command to estimate a Poisson regression model. In Part 2, we compute the estimate of sigma squared. We can use the predict command to obtain the y hat. Then we can compute the mu hat for each observation. After that, we calculate the estimator of sigma squared using the formula. It is 1.39. It is greater than 1, evidence of over-dispersion. The adjusted standard errors are the usual Poisson MLE standard errors multiplied by sigma hat 1.18. That is to say, each corrected standard error is about 18% higher. In Part 3, use the results from Part 1 and 2 and Table 17.5 to compute the quasi-likelihood ratio statistic for the joint significance of the 3 quadratic terms. What do you conclude? From Table 17.5, we have the log likelihood value for the restricted model, minus 2,248.78. Then we estimate the unrestricted Poisson model, which is the model in part 1, we can use the eReturnList command to find all stored results after this estimation. We find that the log likelihood is minus 2168.87. The usual LR statistic equals 2 times the difference between the two log likelihood values. It is 160. The quasi-LR statistic is the usual one divided by sigma squared hat, which is 115. The quasi-LR statistic is high enough to reject the null hypothesis that the 3 quadratic terms are 0. They are jointly significant at any conventional level. Let's solve computer exercise 5. Refer to table 13.1 in chapter 13. There we used the data to estimate a linear model for kids, the number of children ever born to a woman. In part 1, estimate a Poisson regression model for kids using the same variables in table 13.1. Interpret the coefficient on y82. We can first replicate the results in table 13.1 using OLS. Since the dependent variable kids have non-trivial numbers of zeros, we consider estimating a Poisson model. The coefficient on y82 is minus 0.193. It means the number of kids was 18% lower in 1982 compared to 1972. We can use the IRR option for the Poisson regression. The option IRR means incidence rate ratios. That is the e to the power beta instead of beta. It gives the same percentage difference in the number of kids, 18%. In part 2, what is the estimated percentage difference in fertility between a black woman and a non-black woman, holding other factors fixed? In the Poisson model, the coefficient on black is 0.36. It implies that black women have 43.4% more children than non-black women, other things being equal. In part 3, obtain sigma hat. Is there evidence of over or under dispersion? We can calculate the sigma hat manually. It is 0.94. It is evidence of under dispersion because it is smaller than 1. In part 4, compute the fit values from the Poisson regression and obtain R² as the squared correlation between kids and kids hat. Compare this with the R² for the linear regression model. We have already got the fit value, kids hat, for each observation. We use the correlate command in Stata to calculate the correlation between kids and kids hat. Then we calculate the square of it. It equals 0.121. The R² for the linear regression model is slightly higher, 0.130. Thank you very much for doing the computer exercises with me. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.